Hello everybody, we are back. So in this class we will be studying plasma diagnostics. So plasma diagnostics actually form a very important part of the plasma studies. Without this actually we cannot basically uh, know what kind of plasma we have created, what are the species distribution, what is the temperature, you know these are very much important. What is the velocity of the plasma? So without knowing this we cannot qualify its suitability for any particular applications. As I have already told you, the tone of this course is that we want to go from lab to the industry, and for that we must qualify our plasma suitability for particular applications. And to do that, if we say something people will not believe, we must prove ourselves that okay, we have developed a plasma source which has this much temperature, which can offer you these are the species which will be useful for your application, or which can do something which is not possible to be done at by some other means, or it has some superiority over the competing techniques that are in practice. So plasma diagnostics basically we will be trying to know the plasma temperature and species distribution, which is very much important. Then of course the dynamics of the plasma and how the plasma evolves with time. So as I told you that plasma phenomena are happening over a vast scales. This scale involves the time scale as well as spatial scale. You know, whenever you are exciting an atom, the emissions, the electronic level transitions, they are happening at very short time scales. The lifetime of the states and the transition that happens, some metastables are of course there, but typically you can consider that those phenomena are happening in the nanoseconds time scale. Whereas if you are going to understand the fluid dynamic instability, definitely the scale goes on in second. So the issue is that how to cover such a vast range of time scale, and you need to have some equipment which will be able to grab the phenomena that is happening so fast. So we have limitation. We are not very much equipped to diagnose so easily as we go shorter and shorter time scales. It is rather easier to grab the picture in seconds, milliseconds, microseconds. But when you want to go for nanoseconds, then you need to develop some special techniques to grab those things. So many times we are not able to grab those, and we need to go for modeling that this may happen, that may happen. So hypothesis kind of thing. Then when you are going to measure something in the time scale, you know that this scale ranges from the atomic scale to the scale of meter. So you are again going from 10 to the power minus 10 meter to 1 meter. This is again an enormous scale, and it is that it is very difficult to probe a single atom. Of course, there are techniques nowadays, but on a small scale, in an industrial plasma regime, if you want to go for that, it is really difficult. So when you combine both these two, the time scale as well as spatial scale, then definitely you are going for the fast imaging kind of thing. And what is the range that is available? Your normal photographic camera, which is available in your cell phone, you can grab say some in a second, one or two. But if you are going for 100,000 and say hundreds of thousand, then you can see the difficulty that is. But nowadays the technology is advanced, and you know we can grab 10 to the power 6 frames per second as well actually. So that is not a problem nowadays and advanced technology. So we will be exploring those things and the different techniques in this class of plasma diagnostic. Now there are two types of plasma, one is your thermal and one is non-thermal. Then again, diagnosis, when you are going to do that thing, suppose somebody has some fever and they want to know the temperature. What they do actually, they put a thermometer uh, in your mouth and they get the temperature that is there. So it is an invasive. So you are basically putting your diagnostic probe inside the region where you want to measure the temperature. Sometimes, it is not possible, just not possible in plasma. Like, plasma is having a temperature which is in excess of 10,000 degree Kelvin. That I am telling for the gas temperature. So, at that temperature, no invasive probe is possible, because the moment you put it, it will get evaporated. So, not possible. So, we need to go for some technique which are not invasive, like OES, that is optical emission spectroscopy. So, you are getting the information about the system from outside without invasive, without disturbing the system. Now, there is another thing actually. The moment you put some probe in for inside the system for measurement, you basically disturb the measurement. So, whether it is a small or it is a large disturbance, that depends on the kind of measurement you are doing. But the moment you try to know what is there, you are disturbing the system itself. So, it is always better to have diagnostic with non-invasive techniques like the optical emission spectroscopy. Here you are getting the information about the system from the radiation that the system is emitting, and because we know the physics of emission of the light, and there is also some modeling aspects are there, because what are happening and how they are emitting, that again has some assumptions. So those things we will be discussing in this problem. Like, this Abel inversion technique is required when you want to measure the temperature for a broad plasma source. Whereas if there is a very steep gradient like arc and a very thin plasma, you can very well measure the axial temperature distribution without doing Abel inversion. So there are ways actually to circumvent the problems. Then, the species density. Nowadays, spectrometers are available, and the species, puts their signature on their own in the spectrum. So, by looking at the spectrum very carefully, we can very precisely tell which of the pieces are present there. But just knowing the pieces is not sufficient. You want to know their concentration. So, if you want to know that, again, that is a bit involved job, because knowing the exact concentration depends on many other parameters. Again, you need to go for modeling. So, this is for your in general, for thermal plasma cases. When you go for non-thermal plasma, of course, you can do invasive measurement, because there the gas temperature is quite low. But in doing so, again, you are inserting the probe, and the probe is usually a metallic probe, and that can disturb even your non-thermal plasma, the cold plasma, because when it get bombarded by ions, or it is heated because of the drawing current, or the flow of your species within that device, within that probe, become influenced by the external magnetic field that has been applied, then your results become different. So, finding the accurate information about the system is bit tricky, and you should be wise enough to apply all these diagnostic tools in proper manner, so that you get the right information about the system. So, all these things are basically subject of this study in this class, and we will be continuing in the next class, the plasma diagnostics. So, before we enter into that, we were discussing the plasma seed. Okay. And that discussion is very much necessary, especially when you are going for the invasive probes. Like in cold plasma, you are putting some Langmuir probe over there, and you want to understand the behavior of the probe. under biasing. So, in those cases actually it is very important to know the plasma sheath formation, because that is the region is very thin and very difficult to probe experimentally. You need to go for modeling, and based on your knowledge you tell, okay, this is the result that we are getting about the system. Okay, so we'll enter into that, but before we reach there, we finish one slide on the plasma sheath that we were discussing in the previous class. So what we are discussing, that Bohm's criteria for sheath formation, and what we got in the previous class, that this condition, that 1 minus 1 by twice y0 should be greater than 0. So how we got that? We had this expression that d2 d chi by d psi square, the left side was 1 square and the right side was also a square. So this part, what is there before this chi square, this also should be positive, because this is positive squared quantity, this is positive squared quantity, and this also must be positive. So that was giving us that 1 minus 1 by twice y0 should be greater than 0. So this is giving us y0 greater than half. Okay. Then what is y0? What is the value of y0? So y0 was that, if you see the definition, so y0 was mi vz square by twice kte. So this is greater than half. Okay. So half will cancel, this part is y0 and that should be greater than half. This means that this 2 and 2 will cancel and vz square should be greater than kte by mi. So that is what you have got over here, that kte by mi, vz0 greater than kte by mi. So this velocity, kt is half mv square and will cancel, and then this is having the dimension of velocity. So vz0 should be greater than v Bohm. This is the Bohm velocity. So the ions must enter the sheath region with a velocity greater than the Bohm velocity, so that the sheath formation takes place. The problem arises because electrons are very fast in movement. So even though your wall is getting negatively charged, they are so energetic that they can reach much more than the ions. And ions, unless they start moving with certain velocity which higher than certain value, they will not be able to catch up with the electrons and will not be able to form a positive sheath region. Okay. Now, when we plot this NE and Ni as per the expression that we have obtained over there as a function of this chi, then what we are getting, that when y0 greater than half, that is the condition that has been maintained for the Bohm criteria, you see that Ni is always greater than Ne. You are seeing that all the regions it is over there. And as per our actually criteria, because we want that both electrons and ions will be same in number density at the edge, so they are all matching together with 1. So Ne equal to Ni equal to 1. So that is there. So whatever they are reaching, so no additional charge is entering into that region. Now when y is equal to 0.5, then what is happening? Then you are seeing that this Ni and Ne, they are same only exactly at the wall, but when y0 less than half, that is this is not maintained, okay, y0 less than half, then you are seeing that this Ne is more in the region very closer to the wall compared to the Ni. So there is no question of formation of this positive space charge region, positive sheath region. So this sheath doesn't form. So physically also we are able to see that this sheath formation is possible only when Ni is greater than Ne in this region, because of that uh, this negatively charged wall, the electric field that has been created, that is retarding the electrons and accelerating the ions. And when they are able to completely retard the your electrons, that cases are happening, that when y0 greater than half, that Ni is substantially high compared to the electrons, even though they are energetic, and that is why the positive sheath region is forming. Okay, so this is how the expression for any Ni goes, and the physical formation of the sheath that happens near the sheath near the wall. Okay. Now we come to the diagnosis of plasma, uh, temperature and electron density in thermal plasma. So these two parameters are very much important. One gives you its capability to do the process at very high temperature, and the other one is giving you the species density that are there within the plasma. So electron density is one of that, and you know that other species whichever is present there you can get through the emission spectrum via some spectrometer. So I will be coming to that. Now typical setup for this plasma diagnostics for thermal plasma looks like this. This is emission spectroscopic setup. So what are there in that? Let us see very carefully. So this is one, the plasma torch. This is the jet that is coming out, and you are interested in knowing the central axis temperature in this case. And you are using a spectrometer, this 8 number is spectrometer, and the data that has been collected by the spectrometer is getting recorded in this computer, which is having a software compatible with the spectrometer that you are having and using for recording the spectra. This is a bench where you can very precisely move the fiber which is collecting the light. And usually what we do, we place one lens in between the plasma jet and the collecting optical fiber, so that the distance between the point where from you are collecting the light is 2f. F is the focal length, so double the focal length, you keep the distance. If this is the case, and if you go to your school days optics, then you will see that in such case you get equal magnification on the other side but an inverted image. So the image of this jet is exactly from here, but it is inverted. So the nozzle exit will be in this side, and your jet end will be in this side, but the point will be same. Okay, but magnification is same. That is another very important thing, because 1-to-1 correspondence you get in that case. So you are getting the light collected from the center and getting impinged on the tip of an optical fiber, and that light is collected by this optical fiber 10, and that is coming to the spectrometer 8. Now here there are two things. One is aperture control and another is a lens. Okay, 11 number is the lens, and 12 number is actually aperture control. Why this aperture control is required? Because the amount of light that is collected by the fiber, it may be very high, which may cause saturation of the spectrometer CCD. If CCD is saturated by the intensity, then you will not get the variation of intensity of different spectral lines. You will get all at uniform temperature. So that is of no use. So you should control the intensity in such a way using the aperture 12 that you get the spectra without any saturation. And the optical bench, this number 9, allows you to move this fiber as per your wish at specific axial location where you want to measure the temperature. So this is the case for the uh, optical emission spectroscopy uh, of thermal plasma jets. Okay, this is a typical configuration that we use. Now, as the spectrometer is concerned, I don't know how many of you actually seen a very sophisticated spectrometer. Nowadays, they are available in very compact form, but the physics principle you all know. I am sure about that. So the thing is here. This is the optical fiber port. So the optical fiber, this one, that is taking the light from the plasma coming here and entering into this port. So this port now I am showing you. So this is the port, the entrance of the optical fiber. So the light is getting coming from here through the optical fiber. The light where from it is coming? From the exact axial location that your optical arrangement allowed you to collect from. Now this light is coming and then this is falling on a collimating mirror. Okay, and this collimating mirror is focusing this over a grating. Okay, this is just reflecting this over a grating. That grating is now dispersing different colors at different angles. Okay, and this is now dispersed spectrum, and that light is falling on the CCD spectrometer and at different spatial locations depending on the way it has been dispersed. Different colors have been dispersed. So the same thing, this is shown over here. This is actual spectrometer interior. So this is the entrance slit of the fiber. So this is optical fiber port. What is there in the schematic? You can connect with this one. So the light is coming from here and impinging on the collimating mirror. What is shown over here? So this collimating mirror is now focusing the light, collimating the light over this grating. This grating, you see that the light is white or whatever light is coming, it is not dispersed till this point, But when it just impinges on the grating disperses it. So you are started seeing the color, the red at one end and the violet at the other end. So this dispersion is in physical space. So this dispersion allows different wavelengths to fall at different regions of the this one is focusing mirror of the mirror. Then this mirror focuses different wavelengths at different regions of the CCD, the charge coupled device. So when it falls on the CCD, the intensity of red light, intensity of the blue light, if at all they are there, they will be showing their presence. And if they are very strong, suppose in red, the red region will be having very strong intensity. If suppose something of yellow color is not there present, so that part will not get any intensity over because no wavelength is there. So no wavelength is dispersed at the getting dispersed at that location of the CCD. So CCD is not producing any intensity corresponding to the yellow wavelength. So that is just for example. Suppose in blue they are having very highly intense one emission. So there they will get this region very high intensity in the CCD camera. But what is important to understand is that this intensity variation is occurring at different spatial location. Now a photon of blue color when it is falling on the CCD and a photon of red color when it is falling on the CCD, that will generate electrons may or may not be of same intensity, number of electrons that is getting generated. So they are called quantum efficiency. So so depending on the kind of material that you have used and their response, you will get different current that has been generated at different locations. So those current ultimately give you some voltage at different locations, and that will be measuring through your computer. So that will be basically sensed. Now, you know that sensitivity of a material, photosensitivity of a material that is there in the CCD which has been used, that may not be same for all wavelength. So, what we need actually, we need to ensure a material, and we should ensure a wavelength range over which the response is more or less constant. Okay. So, if that is the case, then what intensity you are getting through the CCD, they are reliable. Otherwise, because of the photon response itself, if you get more, current at certain location rather than, certain wavelength where even though the intensity is high, response of the photosensitive material is not that good, then you will not get that much signal over there. So, in one case, although the intensity is less, you are getting a higher signal because of the photosensitivity of the material. In other case, you are not getting that much signal even though the intensity is high. So, that matter is important, and so people are developing different kinds of photosensitive materials, these CCD materials, and they're trying to have the efficiency of with respect to the wavelength. They are more or less, they are getting a flat response, and if you are getting a shorter wavelength region, you are analyzing, then it is expected that you will get more or less a flat response over that region, and that is what is expected actually, what you should look for, so that you can get more accurate measurement. So, this is as far as the spectrometer is concerned. What it is doing, it is getting the light, whatever it is coming, whatever the wavelength content is there in that light, then they are ultimately what they are doing, they are focusing that over a grating. Then grating is dispersing different wavelengths at different spatial locations, and at that location the CCD material is there which is generating signals depending on the intensity of the wavelength, and photosensitivity of that material should be uniform over the wavelength range so that you get reliable signals, and they become proportional to the number of photons that are falling, the intensity of the wavelength at that for that corresponding process actually. So, what you get finally, you get an electrical waveform that is proportional to the intensity of the wavelength. Now, what I say that the intensity, this has been written in arbitrary unit, because the intensity what you are finally recording as a voltage signal, that will depend on many other things, like you see the intensity of the light which is coming. It has basically very vague meaning in terms of intensity, because if it is a suppose we are using a an older fiber, so the transmission loss will be more, or suppose some dust is accumulated over somewhere, then the signal will be absorbed. So, the intensity what you are getting finally at the CCD end, it is basically relative intensity, it is not the absolute intensity, and that relative intensity is sufficient for us for this measurement, that will explain. So, now the technique that I will be explaining you for emission spectroscopy of uh, thermal plasma is called Boltzmann plot technique. And how this technique arises, what are the basic principle behind that, that is very simple, and I will tell you how you can use this kind of spectrum that you record like this one. So, different wavelengths has been different intensity, you are seeing that at 700 to say 740 the intensities are quite say less, and then as you move on to higher wavelength, you are seeing that the stronger intensities are present over there, and that the wavelengths whatever you are getting, they are very fixed for fixed atoms. So, when an argon atom is emitting, then these are signature of the precise energy levels that it is having. So, whenever you get this set of lines, we call these as spectral lines, they corresponding to transition from one level to another. These are atomic transition lines. Whenever you get this signature, whether you get in India or you get in US or you get in France, they will always remain the same. So they are basically signature of the spaces. Just seeing this kind of distribution of lines, wherever we get, we can tell with 100% confidence that argon atoms are present in that source, because we are getting this set of lines which are uh, due to argon alone. No other species can simultaneously generate all these set of lines when they are excited. So these are basically signature of the species, and in a plasma what are the species present we identify just noting the spectral lines that we record from the emission spectrum. So I stop here, and in the next class I will be explaining how we actually do the Boltzmann plot and how we extract the temperature from that, what is the principle behind, and what care should be taken to measure the temperature precisely, and what are the other information that we require to measure the temperature, and if there is any issue whether this is universally applicable or we need to modify the technique for some other plasma systems. So we will discuss all these things in the next class. I stop here.